I need to make sure that my mic is on. It was last Tuesday, my EGR356 course. I forgot to turn my mic on. So I have to re-record it. Or use, the one of the recordings that I did earlier, maybe last year, the year before, or 2020, when there was a pandemic. I need to see which one has best recording. Okay, so this is a summary of moving boundary work. So the second exam is going to cover from this moving boundary work. There will be no compressibility chart, because I think it is less important than the other parts in chapter 3. So this moving boundary work, there will be at least one problem, and energy balance equation for a closed system, there will be one problem, and at least two problems in chapter 4 and chapter 5. Okay, so this moving boundary work is important. And this is the summary. So there are 5 different ways to determine the moving boundary work. The first one is when we have a constant volume process, then there is no moving boundary work, because constant volume, there's no boundary is moving. And if it is constant pressure process, this is how you determine the moving boundary work. If it is constant temperature process, this is how you determine moving boundary work. If it is none of these three, then you can assume that it's a polytropic process, and this is how you determine moving boundary work. If you can't determine moving boundary work among these 4 ways, then the final solution, final result is going to be using a graph, PV diagram. So if you can determine the area under this process from 1 to 2, that's going to be the absolute value of this moving boundary work. Then you need to determine the sign of this moving boundary work depending on whether it is expansion, positive, or compression, or negative. So that's how we can determine a moving boundary work. This is what we did last week. And we solved one easy problem. And after you solve an easy problem, what's next? Solving a little challenging problem, right? So let's look at this problem. A piston cylinder device. Why piston cylinder device? Because piston cylinder device, the volume can change. Doesn't mean that we are analyzing, an engine or something. Just piston cylinder device is the easiest concept that can change its volume. That's why we always say either rigid container or piston cylinder device. Okay, contains 0.15 kilograms of air initially. Okay, so we have an initial condition. Need another switch paper. This is my treasure box. I have scratch papers and pens and everything. And 2 weeks ago, somebody took them all. I restarted last week. Okay, so we have initial state number 1, and the pressure T1 is 2 megapascal, and temperature T1 is 350 degrees Celsius. And the mass of the system is 0.15. This is air, and whose mass is 0.15 kilograms. Now it's going to, undergo an expansion process isothermally. What is isothermally? When temperature remains constant. So T is constant. In this process, after this process, temperature remains constant, so T2, the final state of this process, is going to be 350 degrees Celsius. And the pressure is known, P2 is 500 kilopascal. That's not the end of this problem. We have another process followed, that is a compression process, polytropically. So we have a polytropic compression process. PV to the power n is constant. That is polytropic process. And the polytropic exponent is 1.2. So this one is 1.2. So how can we use this equation? P2V2 to the power n is number 3, the final state of this process. P3V3 to the power n. We can do that. And finally, compressed at constant pressure to the initial state. Oh, we have one more process. So there's a process number 3. Compressed polytropically with this polytropic exponent 1.2 to the initial pressure 2 megapascal. So P3 is 2 megapascal. And finally compressed at constant pressure to the initial state. So it's a constant pressure. P is constant. Determine the boundary work, moving boundary work for each process and the net work of the cycle. Then how can we determine the net work of the cycle? The sum of all the moving boundary works is going to be the net work of the cycle. This one is cycle. One process, second process, third process, coming back to the initial state, it becomes a cycle. Okay, so let's determine the moving boundary work of each process. So how can we do that? The first process is constant temperature process. How do we determine the moving boundary work of constant temperature process? This equation. WB is PV natural log V2 over V1. So I'm going to write this equation here. WB, moving boundary work. However, we have 3 moving boundary works between process 1 to 2, process 2 to 3, process 3 to 1. So there are 3 moving boundary works. So this one is going to be moving boundary work from 1 to 2. Can be determined by this equation. PV natural log V2 over V1. Okay. Then how can we determine the moving boundary work? Let's see. Do we know V1? We do not know. Do we know P? Yeah, we know P1 and P2, but we do not know the volumes at the initial state and the final state. So we need to determine the volumes. Then do you know any equation that has volume that you studied in this course? Any equation that has volume? PV is MRT, the ideal gas equation. Then, can we use this ideal gas equation? This is air, so yes, we can. So let's use the ideal gas equation. PV is MRT, and how can we solve this PV MRT? Can we use T1, T2, T3, and everything all together like a buffet? No, you need to select one state and then use only the properties at a state. So you can apply PV-MRT at state number 1, and you can apply PV-MRT at state number 2. You can apply PV-MRT at state number 3, but you cannot mix them. Okay? So let's use this PV-MRT at the initial state. That means P1 V1 and MRT1. Why don't I say M1? Because it's a closed system, mass remains constant. So there's no M1, M2, M3. What about this R? Why don't we say R1? Because R is a gas constant, always the same. So what is P1? 2 megapascal. But always stick to the same unit, not to get, not to make a mistake in the calculation. Always use kilopascal. So instead of 2 megapascal, you can say 2000 kilopascal. What is the mass? 0.15. 0.15. What about this gas constant R? Do you know how to determine this gas constant R? Yes, universal gas constant R bar over molecular weight. Then where can you find this gas R bar? It's always the same number, 8.314. What about this molecular weight? You can go to table A1. Table A1. What about the molecular weight? Molecular weight is this capital M. This is not mass. Mass is lowercase, right? Air, the molecular weight is going to be 2897. 2897. But you can just memorize the gas constant for air because air is one of the most widely used working gases in engineering. So you can just memorize this number, 0.287 kilojoule per kilogram Kelvin. What about temperature? 350 degrees Celsius. Then you can determine the initial volume V1. Am I right? No. Now you know that. Hey, of course. Only two here miss that Celsius in the exam. So that is the lowest number in the past 10 years. So this class is great, okay? So that's why I add so many, the stars. How many stars I added? A lot, right? So 350 plus 273. So that's how you determine V1. Now, can you determine V1? Yes. I have this solution here. So V1 is 0.01341. So V1 is point what? 0.1341 cubic meters. But that's not enough to determine this moving boundary work. We need to know V2. So how can you determine V2? Completely using a new method? No, we can use the same PV-MRT at state number 2. So let's do that. PV-MRT P2V2 M2? No, it's a constant mass. Mass is conserved. P2. So here, what is the pressure? 500. What is the volume? That's what we want to determine. Mass 0.15. Gas constant 0.287. Temperature 350. Not anymore, right? 350 plus 273. Then you can determine V2, the volume at the second state. That is 0.05364. 5364 cubic meters. Now we have everything, ready, and we are ready to determine this WB between 1 and 2. So this V1 is here 0.01341. This V2 here 0.05364. What about this PV? Oops, I don't know whether this one is P1, P2, P3, V1, V2, V3. How can you solve this equation? You can say P1, V1 or P2, V2, doesn't matter. Because when you have a constant temperature process, pressure times volume is constant. That means P1 V1 is the same as P2 V2, is the same as P3 V3, and P2 million V2 million. Remember that, right? So pressure times volume is always the same number whenever you have a constant temperature process. So we can say P1 V1, and this P is going to be 2 megapascal, kilopascal, 2000, and V1, and this number, 0.01341. Then you can determine the moving boundary work between state number 1 and state number 2. And the answer is, do I have it? 37.18. 37.18 kilojoule. Any question about this moving boundary work? What about the moving boundary work between 2 and 3? It's a polytropic process. Whenever you have a polytropic process, how do you determine this moving boundary work? Here, P2 V2 minus P1 V1 over 1 minus N. But that one is between 1 and 2. Here is between 2 and 3. So it's not P2 V2, it's P3 V3 minus P2 V2. So I'm going to write this moving boundary work here. WB between 2 and 3 is going to be P3 V3 minus P2 V2 over 1 minus N. Then let's see. Do we have P3? Yes, 2 megapascal. Do we have a P2? Yes. V2? Yes. 1 minus N, and we know that is 1.2. So let's substitute all the numbers that we know, 2 megapascal. So this one is 2000. P2, 500. V2, this number, 0.05364. And N, it is the polytropic exponent, 1.2. So sounds like, we know most of them except V3. So we need to determine V3. How can we do that? Can we use PVMRT? Not anymore, because we don't know the temperature here. Then do we know any other equation that has V3 other than the ideal gas equation? Do we have any equation that has V3? Do we have any equation that has V3? Right here. Yes, you can use this equation. So this relation, P2V2 to the power n is P3V3 to the power n. P2 is 500, P3 is 2000, V2 is 0.05364, N is 1.2, N is 1.2. Can you determine V3? Yes, we can, right? Yes? No? If you divide by P3, so one way you can do is P2V to the power n is P3V3 to the power n. You can divide each side by P3, and V2 to the power n, V2 to the power n. Then you can cross them out. Then what you have? P2 over P3 is V3 over V2 to the power n. And you can take a natural log P2 over P3 is n times natural log V3 over V2. Then you can determine V3, right? Or if you have a engineering calculator, you can just solve that equation to determine V3. If you don't have, if you just have a very simple calculator, you can convert in this way to determine V3. Anyway, if you determine V3, the answer is 0.0169, 0.0169 cubic meters. That is V3. Then you can complete this V3 here. Sun goes in here. Then you can determine the moving boundary work between 2 and 3. The answer is minus 34.86 kilojoule. Why this one is a positive value and this one is a negative value? Because this one is an expansion process, this one is a compression process. Whenever you have an expansion process, moving boundary work should be a positive value. If it is a compression process, the moving boundary work should be a negative value. What about moving boundary work 0? That means there is no moving boundary, it's a constant volume process. The last one, between 3 and 1, that's a constant pressure process. When you have constant pressure process, how do you determine moving boundary work? Here, pressure times V2 minus V1 between 1 and 2. This one is 3 to 1. So it's going to be P V1 minus V3. Moving boundary work between 3 to 1 is going to be P V1 minus V3. Then do we know the pressure? Yes, 2 megapascal, 2000 kilopascal. V1 here, 0.01341. V3 here, 0.0169. Then you can determine the moving boundary work. That is, do I have it? Minus 6.97. Minus 6.97. Another compression process. Now you can determine the net work of this cycle. So WB net can be determined by this one, 37.18 kilojoule minus 34.86 kilojoule minus 6.97 kilojoule. So the W net is going to be minus 4.65 kilojoule. Any question about this problem? So this one problem has 3 different processes. So you have to determine the moving boundary work for each process and finally determine the net work. So it's like the final boss of moving boundary work. So if you can solve this problem, you don't need to worry about any moving boundary work, right? No question? Okay, good. Let's go to the next. So that's everything about moving boundary work. What's the next? The last part of chapter 3, energy balance equation. The last part, energy balance equation. I think we already discussed the energy balance equation for a closed system. So let me give you a summary. We have 7 minutes. That's plenty of time. We can cover the entire chapter 3 and then go to, have lunch and come back and continue. So if you have a closed system, how can we determine the energy balance equation? It's always the same. Conservation of energy principle. You remember that story, eating 5 hamburgers and etc., right? So energy transfer into a system minus energy transfer out of a system is the change of energy of a system. This is the conservation of energy principle. And we studied there are 2 energy transfers. One is heat, the other one is work. So we have a heat and work for this incoming energy transfer. We have a heat and work for this outgoing energy transfer. So we can say heat, Q in, and work, W in, and we have heat, Q out, and work, W out, that goes out of the system. Is going to be the change of energy of a system. How do you determine the change of energy of a system? How do you determine the weight change before and after you eat in a buffet? You measure the weight. Before you're having it, you measure the weight. After you completely full, right? So it's going to be the total energy at the final state minus the total energy at the initial state. And how do you determine this total energy? Mass times specific internal energy U plus specific kinetic energy V2 square over 2 plus specific potential energy gravity times elevation Z2 minus mass times the initial state U1 plus kinetic energy V1 square over 2 plus G times Z1. So that's how you determine the energy change of a system. And usually we neglect kinetic energy change and potential energy change. So you can neglect these two. Then what do you have? You have mass times U2 minus U1. Then you may remember that we studied moving boundary work. It is actually this W out, but should be a part of this change of energy of a system that we discussed last week. So we need to add moving boundary work at the end. So Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1 plus moving boundary work. This is the general form of energy balance equation for a closed system, but there are, the way to simplify this one. The first one, what about you have a constant volume process? Constant volume process. If you have a constant volume process, what is the moving boundary work? 0. So if you have a constant volume process, the right-hand side is just mass times U2 minus U1. Now, this is more important. What about if you have a constant pressure process? What is the moving boundary work when you have a constant pressure process? When you have a constant pressure process, moving boundary work is going to be P V2 minus V1. That is moving boundary work. Then, this right-hand side becomes, since the moving boundary work is P V2 minus V1, the right-hand side becomes mass times U2 minus U1 plus this one, P V2 minus V1, but we are using lowercase. Can we use lowercase? Yes. P mass times specific volume. Mass times specific volume. Can we do that? Yes. P mass times specific volume minus mass times specific volume. Now we have a mass, mass, mass. Can we take mass out of it? Yes. Mass times U2 minus U1 plus PV2 minus PV1, right? Then we have subscript 2, 1, 2, 1. What about this subscript? Is it P1 or P2? Constant. So it can be P1 or P2. Doesn't matter because they are the same. So we can say it's P2, it's P1. No problem because P1 is P2. We're talking about constant pressure. And these two together. These two together. What is U plus PV? Do you remember? What is U plus PV? We studied it last week, the week before. Enthalpy, H. So this one is enthalpy H2. This one is enthalpy H1. So mass times the change in enthalpy is H2 minus H1 is the constant pressure. One more minute, and you may remember we can combine Q in and Q out, W in and W out. So these two together, we can say Q. These two together, we can say W. However, this Q is Q in minus Q out, but this W is W out minus W in. So there should be a negative sign. So these are the energy balance equations. So the left-hand side, you can use this one or this one. The right-hand side, this is the general form. If it is constant pressure, this one. If it is constant volume, this one. If it is constant pressure, this one. So this is the energy balance equation that you can use. That's all for today. Thank you, and see you next week.